Okay, so layer model. This is one of the more popular models for CSH. I talked about creep yesterday, one of the models that you can use to explain phenomena of creep. So you have layers of CSH and it's calcium silicate hydrate, right? So water has to be there, and you have water in between those layers, and I told you that about 18 angstroms is a spacing between these layers or solid systems, or the gel pore size. So basically when we talk about gel pore, you are talking about a size of 18 angstrom. 18 angstrom is 1.8 microns, really small. So you have layers, you have water in between the CSH gel. This is called the interlayer water. Water in between the layers is called the interlayer water. The water that's absorbed on the surfaces, they are held on to the surfaces by a theory of adsorption. Have you heard of the BET theory? Bruno, Emmett, Teller, BET. I'll show you some BET theory issues. That water is called adsorbed water, which is held on the surfaces by van der Waals forces. And then inside this whole big pore, that's your capillary pore, very large capillary pore, right? So when water drains, and this model has a lot of implications in how properties of concrete develop. Okay, so when you want to measure degree of hydration, you want to measure how much of cement has hydrated, right? So you do non-evaporable water for degree of hydration, right? Have you done that? So if you do non-evaporable water for degree of hydration, you're looking at how much of water in this system is non-evaporable, which means how much of water will go away only if you heat it to a very high temperature. At the boiling point of water, now there is another physics behind this. When you have water in any pore, in concrete, where is the water? In the capillary pores and all these pores, right? What is the boiling point of water? 100 degrees Celsius. So theoretically, if you heat something at 100 degrees Celsius, all the water should escape, should boil and go. It will not. Why? No, so forget about steam. Steam is fine. 100 degrees Celsius, water, you have given enough energy for water to change its state from liquid to gas, right? When the water molecule is not constrained by anything else. You leave the water free, when you give a heat equivalent to 100 degrees Celsius, it will change its phase from water to gas. But if you are constraining water in small pores, this is like holding somebody trapped in a room, holding somebody trapped in a small place. 100 degrees Celsius is not enough. You need to give even more energy for that attractive bond between water and the surfaces to break. You guys know about capillary surface tension, right? So there is a lot of surface tension forces between water and the walls of the capillary. You have done the test tube experiment for surface tension, right? There's a lot of forces between water molecules and the wall of the pores. You need to give even more energy to escape. So at 100 degrees Celsius, 105 as per your standards, all the water in the capillary pores will go away. And this capillary pore water, is this water, did that contribute to hydration? No, it's just staying there, right? It did not involve itself in any hydration products. But this water, the adsorbed water and the interlayer water, are part of the structure. They are part of CS. They are the edge of CSH. So if you want to know degree of hydration, you want to find out how much of H is there in CSH. And if you look at books, when completely hydrated, how many grams of non-evaporable water can you get in 100 grams of cement? When I take one particle of cement, I hydrate it completely. 1 gram of cement, I hydrate that 1 gram of cement completely. It all changed to CSH. How much water will be here and here? You remember that number? You should remember that number. 0.23. 23 grams of water in 100 grams of cement is your non-evaporable water if all the cement has hydrated. Now, if I burn this sample from 100 degrees Celsius to 1000 degrees Celsius, I am removing all this water, right? So, you know how much is the mass loss. You divide that mass loss by what is the mass loss for pure 100% hydration, that's 0.23, you get the degree of hydration. Is that how you not calculate degree of hydration? So this is one way. So this layer model is the basis for calculation of degree of hydration. This is what they use. The layer, the adsorbed water and the gel water are the only two water available as hydrated water. The rest is all capillary water which will escape very easily. Okay, water interacts with CSH through surface bonds. Water can access the interlayer region, you've seen it. Rearrangement of CSH possible when water is removed. Now think about it. I have these layers of CSH with water in between. What happens if I remove water from that layer? Now, how can I remove the water from those layers? I have these layers of water, layers of CSH with water molecules in between. How can I remove the water? By heating. What's the other way to remove that water? Pressure. By applying a squeezing pressure, right? What we call that, if you apply a squeezing pressure for a long time, what do you call it? Creep. Right? Creep changes the structure of CSH. Because of creep, because of very heavy load that's acting for a very long period of time, water molecules squeeze out of CSH, your CSH gel starts to rearrange. When CSH starts to rearrange, CSH is what is providing the volume for this whole thing. When that thing starts to rearrange, volume changes like creep starts to happen. So creep CSH lies at the heart of the whole mechanism of creep. So you can remove this by water. So internal rearrangement is possible. And changes in bonding causes permanent structural changes. So these are all different types of chemical bonds that you have inside. Changing those bonds causes changes in structure, in the structure of the material also. Early and late product CSH, the inner and outer product, we talked about that. The early outer product CSH, the early product growing out from particle surfaces. It's a low density product, higher porosity, variable composition, also called ground mass, but nobody calls it now. Late product CSH, after hydration becomes diffusion controlled, CSH forms as a denser mass around cement grains. Coating thickens with time, they're called phenograins, denser and more stable. So inner product is more denser, outer product is less dense, but outer product forms first. Only after outer product forms, then you have diffusion control reaction and then inner product. So that's calcium hydroxide. If you look at sheets of calcium hydroxide, you see all the sheets of calcium hydroxide forming on the surface of a hydrated cement particle. And this side, what is this? There's a big capillary pore right next to it, right? See the layers of CSH, and typically you can see large masses of CSH forming, because when one nucleates and forms, that acts as the surface for the next one. So it's sometimes you see layered CSH structures. So this length is 20 microns. I don't know what magnification is. So this length is 20 microns. So the sheets are roughly 10 microns big. I mean, magnification is, as long as, typically people do different ways. People do magnification, but this scale bar is more used. You want to know what the size scale is. It doesn't matter what magnification is. Sometimes people remove that. I typically, when I publish, I remove every other information except the scale bar. Because what happens is, some people will look at it and say, oh, you have looked one at 300 and one at 500, so they are different. So they're not really different. And people will get confused. Why do magnification? Why bother? Just show only the scale bar. So you can see here, these calcium hydroxide crystals are 200 to 300 microns in size and about 10 to 15 microns. 20 to 25% of the base volume. Nuclei can grow within the capillary pore space, will only grow when free space is available. Temperature of hydration influences the formation and morphology. This is ettringite, calcium aluminosilicate hydrate. Again, you can see here all elongated grains. Calcium sulfoaluminate, minor constituent by volume 10 to 15%, ettringite, well dispersed throughout the paste. And this is another kind of feature called Hadley grain. Some of you might have seen it. It's kind of an artifact of hydration. Some people would like it. To see that a grain, a cement grain, has hydrated from within. For some strange circumstances, you see some Hadley grains also. And you see ettringite, monosulfates. Monosulfates sometimes are in the form of some nice architectural flowery shapes. You can see some of those sometimes. Ettringite are needle-like crystals. You can have large needles, small needles. You can have all of that. So, quick summary of what you can see. CSH, CH, ettringite. Typical density. CSH, this is the inner product CSH density. Ettringite is 1.75, monosulfate 1.95. Crystallinity, very poor CSH. The remaining are more crystalline. And the size range is also you have here. Dimensions of solids and spaces. So you see here about 1 nanometer spacing between CSH sheets. I said 1.8 nanometers, right? 18 angstroms is 1.8 nanometers. So you see here 1.8 nanometer spacing between the sheets. The capillary voids, which might be 100 nanometers. CSH aggregation about a micron. Calcium hydroxide 1 to 10 microns. Entrained air bubbles about 1 millimeter, 10 millimeters. If you put all together, one more picture, where did it go? Oh, it's coming probably somewhere else. Okay, so this is the dimensions of solids and spaces. So that is my first talk. I should have finished this yesterday, but better late than never, right? Oh, it works only in the duplicate mode?
Yeah.
You can open the next one, L2. Okay, you can leave it there. Leave it there. No, okay, make it bigger, right? Okay. So far we talked about hydration, we talked about cements, we talked about hydration, we talked about hydration products, we've talked about the individual structure of the hydration products. Basic, everything with respect to cement, mostly, not completely, but mostly, the chemistry part is over. Right? Any questions on, any clarifications on any of these topics before we go further? All be good? Yes.
How to find how much unhydrated cement is there?
I'll do a section on image analysis probably later in the day using backscattered images to find out how much of unhydrated cement is there. But the easiest way is to find out what is the degree of reaction. Use non-evaporable water to find out degree of hydration. If my degree of hydration of cement paste is 50%, 50% cement is unhydrated. That's the easiest way. If you want to use it from SEM images, you can use SEM images to find out. But the easiest way is to find non-evaporable water. If you have a furnace, you can do it. Very easy. Yeah. Good question. When you cut, the microstructure can be disturbed. But what you do is, if you're doing backscatter, microstructure disturbed meaning you might form some additional cracks. That's pretty much it, if you don't cut carefully. But if you really carefully cut with the appropriate tools that they have to cut, there won't be significant changes. There's some slight changes, and then if you polish it for backscattering, you will mask those changes. Generally, you won't find that many changes. Okay, so the next one is how do microstructures form? So we talked about, I'm going to talk about how particles pack. Now you have to take this, you can use your imagination and consider whatever scale that you want. So this I leave to your imagination now. If you want to think only about cement paste, you can think of this as how CSH grains and the calcium hydroxide and the ettringites and the monosulfates and all of them pack together. Right? if you want to think of only cement paste. If you want to think of mortars, you can think of how all the sand grains packed together and in between there is a paste. If you want to think of concrete, you can think of how all the coarse aggregates fill together and how everything else is in between. So this, whatever I'm going to talk now, applies to any length scale in concrete that you want to think of. But what we're going to do is some of the basic theory and the basic understanding of how particles pack, which results in the microstructure formation. Okay. Lattice. So here's some very simple examples to show this basic crystal structure studies to show how different things are arranged. So if everything is arranged in a uniform order, we call them a lattice, right? These are all arranged in a uniform order, and if I take these shaded balls and connect the center of all the shaded balls, I have a cube. So I call it a unit cell. And I say that if I take that one cube and put several cubes like that together, I can represent this entire structure, right? Simplified way. I connect all the centers of adjacent atoms and call that a lattice structure. Now you have three different cubic crystal types, and some of you might have seen this. This is called a simple cube where I have an atom or a particle in all 8 corners. Here is a body-centered cube. I have a particle on all 8 corners plus one particle in the middle. And here is a face-centered cube. I have a particle on all 8 corners plus one particle on all the 6 faces. Now each of those, and this is simplification, each of those 3 simplified representations have different levels of pattern. Okay? So this is the initial start, just to show some simplification. So if you do a simple cubic structure, this is very rare in nature, but if you do that, basically I have a cube and all the 8 corners I have one particle each. Okay? You take a cardboard box and then put one particle in 8 cardboard box, 8 corners, and all the particles touching each other, of course. And the corners of the cube are the centers of particles. Right? So I'll get a structure like that. So if I have all the corners of the cube as the center of the particle, and remember this cube has 6 sides, therefore on all 6 sides I have other cubes like this also. And I have 8 particles in 8 corners. How many particles do I have inside the cube on one side? How many? No, just look at this picture. How many particles do I have inside the cube on one side, on one particle? So here is one particle here on that corner. The center of the particle is the center of the cube, right? And the cube has this side, that side, the other side, all particles. So on all sides particles, and then, so effectively you have only 1/8 of the particle inside the cube. The remaining particles are outside. So if I have 1/8 of a particle on one side, if I have 8 sides, how many total particles do I have in this unit cell? I just have one particle, right? So in that particle I have only, in that cell I have only one particle. If the side of it is A, I can find out what my atomic packing factor is. So this distance is 0.5 A. I can find out my packing factor as 0.52. What does that mean? If I take a cube and take particles that are half the size of the length of the cube and put particles on all corners of the cube and I fill this room with cubes, how much of space am I filling? 52%. Basically what it says is that if I have spheres of the same size and I am arranging spheres of the same size as edges in organized fashion as edges of a cube, I can fill only 52% of the space. 48% stays as? That's one thing. Now if I simplify it into what is called the body-centered cube, a little more complicated. So again you have all the edges have 1/8 atom. There is one big atom right in the middle that has displaced the particle so that the distance now is a little more. And you can do all the calculations I'll skip that, you can look at it. You will get a packing factor of how much? 60. So basically, I put exactly those cubes plus I put one particle in the middle of the cube. Putting one particle in the middle of the cube where I have all the particles makes the cube larger also. Right? So think about that. So effectively, my packing becomes 68%. Now, the other one is face-centered cube. In addition to all the 8 atoms in the corner, I put half an atom on the face, all the 6 faces. So I effectively get 2 atoms in a 4 atoms in a unit cell, and I will get a packing factor of 0.7. Now, with uniform size particles, with one size particles, this is pretty much the nature. If you have just one size of particles that you want to fill, if you get one size of aggregate, you collect pebbles of exactly 1 inch, and I say I want